In this video, we're going to talk about taking the derivatives of special functions. So now that we know how to take a derivative using our power rule, our product rule, or quotient rule, we're going to expand that to some of our special functions, namely the trig functions, exponential, and logarithmic. So remember, if we're finding a derivative of a function, we're trying to find the slope all along that function. So if I'm given the graph of y equals sine x like I have here, I can sketch a graph of its derivative based on the slope. Well, I know at this maximum point it has a slope of 0. At this minimum point it has a slope of 0. And then I have to look at what's happening between those 0 slopes. So as I'm coming along from this 0, I'm going in a negative direction and it's getting very, very negative till here. And then it starts getting less negative and it goes back up and approaches 0. So if I want to sketch that, I see that it's coming down. It gets steep, and then it goes back to 0. Similarly, over here, it's 0, and it's getting steeper and steeper and steeper, but it's in the positive direction. And it's getting as steep as it goes, and then I can do the same thing likewise on this farthest left section. It's a positive slope. Starting at 0, 0, it's positive. It's really positive, and then it's getting less positive. And so we'd say it's coming up over here. Now, if I take a closer look at this graph, we can see this should look like a very familiar graph because this is the graph of cosine. So that tells me that if f of x equals sine of x, by graphing its derivative, I'm able to see that f prime of x is just cosine of x. So these are one of our special functions. When we're dealing with trig functions, we need to know how to take those derivatives. Alright, so we figured out what the derivative of sine is. Let's do a similar technique to find the derivative of cosine of x. So again, here's my graph of y equals cosine x. Derivative is finding what the slope is at all the points. So I know right here, at 1, the slope is 0. At pi, my slope is 0. And at 2 pi, my slope is 0. And so then I take a look again, and I see what's happening between those zeros. So right here, when x is 0, the slope is 0. And then it starts decreasing. So I now have a negative slope and it gets really steep. It's the steepest right here. And then it's getting less steep as it goes back up towards 0. So if I sketch that, we said we're starting at 0. It gets negative. It stays negative. This is all below the x-axis, so it's all negative and then gets steep again. And then I look again. Now I still have a 0 slope, but it's positive. It's getting really steep. And then it's getting less steep, but it's staying positive, which means it's always above the x-axis right there. So again, looking at my graph, cleaning that up just a little bit, I can see the graph kind of looks like this. Now remember, this is just a rough sketch. This is not precise. And we should see this looks really similar to a sine graph, but it's not quite a sine graph. So remember, our original function f of x was cosine x. And we're trying to figure out what is the equation of f prime of x that we drew. Notice it's an upside down sine curve, so this is equal to negative sine of x. Okay, so we can go through that same type of thing to get the derivative for all of our trig functions, but here's a table for you. You do need to know these. Derivative of sine is equal to cosine. Derivative of cosine is equal to negative sine of x. Derivative of tangent x is secant squared x, and you could get that using a quotient rule. If you rewrite tangent as sine over cosine and then go through the quotient rule for the derivative, you would end up with secant squared. Derivative of cotangent of x is negative cosecant squared. Derivative of secant of x is secant x times tangent x. And the derivative of cosecant x is negative cosecant x times cotangent x. So for extra practice, you can get all of these. But in order to be able to do any of these, the two basic ones you need to know are these top two, derivative of sine, derivative of cosine, and all the rest we can get by writing the original problem in terms of sine and cosine and then using our derivative rules. Okay, so just some practice. So I'm given f of x equals x squared times sine of x, and I want to find f prime of x. So notice this is a product. I'm doing x squared times sine x, so I'm just using my product rule. So f of x equals the first times the derivative of the second plus the second times the derivative of the first. Now I'm just going to rewrite that just a little bit because I always like pieces in front. So I have x squared times cosine x plus 2x sine x. And the reason I like to put those out in front is I don't want to accidentally think that I can multiply this x and this 2x and change the angle. The angle does not change. Sine of x is a function, and that stays its own little piece. All right, so another example, f of x equals cosine x sine x. We want to find f prime of x, find our derivative. So again, this is a product, cosine x times sine x, so I'm going to use my product rule. So f prime of x is equal to the first, which is cosine x, times the derivative of the second, derivative of sine x is cosine x, plus the second, sine x, times derivative of the first. Derivative of cosine x is negative sine x. So I clean this up a little bit. Cosine x times cosine x we write as cosine squared x. We put the squared on the function cosine so we know it's the whole thing that's getting squared, minus sine squared x. And if you remember your trig identities, which this is, we're going to start using those. Remember, we did review trig at the beginning of the course. Cosine squared x minus sine squared x is actually equal to the cosine of 2x. This is one of our double angle formulas. So f prime of x is equal to the cosine of 2x. All right, this example makes us use the quotient rule because we have sine of x divided by 1 plus cosine x. So I'm going to say my u is that top function, sine of x, and my derivative of u prime is just cosine x. I like to write out my quotient ones. V, the lower function, is 1 plus cosine x. V prime, derivative of 1 is 0, derivative of cosine x is negative sine x. So to get my derivative, f prime of x, that's low, 1 plus cosine x, d high, so the derivative of the high was cosine x, minus high, sine of x, d low, which is negative sine x, all over the low, 1 plus cosine x, squared, right? Low d high d low, low squared. It's my yodeling time. All right, so now I have cosine x plus cosine squared x plus sine squared x all over 1 plus cosine x squared. And then I say, oh, wait a minute. Cosine squared x and sine squared x, that's another one of those identities we're supposed to know. That's the Pythagorean identity. And that's just equal to 1. So I have cosine x plus 1 over 1 plus cosine x squared. And so this simplifies because cosine x plus 1 over 1 plus cosine x is just equal to 1. So I have 1 over 1 plus cosine x. So here is my derivative. Okay, again, now we're going to start with f of x equals sine of x. And now I want to find f double prime. So that just means find the second derivative. So I'm going to do it the whole process twice. So we know the derivative of sine of x, so f prime of x, is just equal to cosine x. And now I take the derivative of this piece. So now I'm doing f double prime of x. So the derivative of cosine is negative sine of x. Okay, so here for a reference is all of those trigonometric identities. You have all of your reciprocal identities. Up here that we need to know are Pythagorean identities. Again, the one I think that is the most important to know is to make sure we know sine squared x plus cosine squared x equals 1, and the others fall out of that. We have our sum and difference identities. We have our double angle identities. We have our half angle identities. So we used this cosine 2x equals cosine squared x minus sine squared x earlier. These, you can find these in your book. You can find them in tables. If you do a Google search for trig identities, you can get pages of tables of these. Make sure you have these handy if you don't know them off the top of your head. We do need to use these, especially as we start getting into more complicated derivatives that we might need to simplify. Okay, so we worked with special functions. We worked with our trig functions. So now we're going to move on and we're going to find derivatives that are involving the natural log of x, ln of x. So instead of working through the whole thing, I'm giving it to you. If f of x equals the natural log of x, then the derivative, f prime of x, equals 1 divided by x dx times the derivative of whatever this thing is. So if I have f of x equals the natural log of 3x, I'm going to say f prime of x is equal to 1 over 3x times the derivative of 3x with respect to x. So this is just like what we were doing. We're adding on an extra step. So this is 1 over 3x times the derivative of 3x is just 3. So I end up with 3 over 3x. So my derivative ends up being 1 over x. We can also use our product rule, our quotient rule, any of our rules when we're dealing with derivatives involving a natural log. So here we have f of x equals x times the natural log of x. So this is a product rule because I have x times natural log of x. So my derivative, f prime of x, equals the first times derivative of the second. Derivative of natural log of x is 1 over x, plus the second, natural log of x, times derivative of the first. Derivative of x is just 1. So x times 1 over x is 1. Natural log of x times 1 is natural log of x. So this derivative is just 1 plus the natural log of x. And of course, we can also use our quotient rule. So to find my derivative here, f prime of x equals the low function, which is natural log of x, times the derivative of the high function, derivative of x is 1, minus the high function, which is x, times the derivative of the low function, which is 1 over x. And that whole thing is divided by the lower function, natural log of x, squared. And then I just clean that up a little bit, so this becomes the natural log of x minus 1 all over the natural log of x squared. And unlike with a trig function, I'm not going to put the squared onto the ln. I'm going to leave it written just like that. Well, if we take the derivatives of logs, that means we also have to work with exponents because logs and exponents are just inverses. So here we have the derivative of e to the u of x. So that means the exponent could be any kind of function. Its derivative is itself, e to the ux, times the derivative of whatever that exponent was. So let's take a look at a couple of those. So the first one, I have f of x equals e to the 1/2 x. So that means f prime of x is equal to itself, e to the 1/2 x, times just the derivative of 1/2 x, and the derivative of 1/2 x is just 1/2. So I would write this as 1/2 e to the 1/2 x. Okay, the second one, g of x equals x times e to the 2x. So now I'm involving the product rule as well. So g prime of x is equal to the first x times the derivative of the second. Well, that's going to be e to the 2x times the derivative of 2x is 2, plus, then I do the second times the derivative of the first. So I can clean this up just a little bit. So this becomes 2x e to the 2x plus e to the 2x. If I wanted, I could factor out that e to the 2x and make this 2x plus 1. Either of those is acceptable. Well, the exponential function using e as a base is a generalized case, but what if it's a different letter? What if I don't have just the number e? What if I have b or pi or a q or a 3 or a 7? In that case, if I'm taking the derivative of b to the x, b has to be greater than 0, but b is not allowed to equal 1. As long as those hold, the derivative of b to the x will always be itself, b to the x, times the natural log of the base. So if I have f of x equals 3 to the x, the derivative, f prime of x, is equal to itself, 3 to the x, times the natural log of the base, which is 3. Okay, doing another one. F of x equals 7 to the x, so f prime of x, this is exponential, is equal to itself, 7 to the x, times the natural log of that base. Now, this actually is working. If we're looking at this going, well, how come it's different for this than it was for when we had a base of e? It's actually not really any different. If I have f of x equals e to the x, and I followed this same rule because e is greater than 0 and e doesn't equal 1, it would be itself times the natural log of e, but the natural log of e is just equal to 1, so we would just get e to the x. Okay, so we've looked at all of our special derivatives for special functions. We also need to look at limits for some of these functions, specifically the trig limits. Now, if you go into the text, you can look at where these come from, and they do derive them all for you, but to keep the video a little bit shorter, I'm just going to give them to you. We have the limit as x approaches 0 of sine of x divided by x is equal to 1. Now notice I couldn't do direct substitution here because I'd get a 0 in the denominator, it would be undefined, wouldn't work. So we can go through a process, we can get to that one. The other one is the limit as x approaches 0 of cosine x minus 1 divided by x. That limit is always equal to 0. Okay? And we use these sometimes to help us evaluate other limits that can be similar or can at least be rewritten in terms of one of these two. So in this case, we want to evaluate the limit as x approaches 0 of sine of 7x all over 7x. Well, we know from that last slide that the limit as x approaches 0 of sine x divided by x is equal to 1. Well, remember, x is a variable. I don't know what's in that. So for all I know, I could have written this as the limit as x approaches 0 of sine, I'll go with diamond, over sine diamond, or excuse me, over diamond. Let me erase that. I said that wrong. There we go. Over diamond. And I know that that thing is going to equal 1, right? All I did was change my variable from x to a diamond. So what that's saying is I don't really care what that is inside. I don't care if this is a diamond, if it's a heart, if it's a gift box, if it's an X. It's saying as long as they match, this limit has to equal 1. So my limit as x approaches 0 of sine 7x divided by 7x is just going to equal 1 because these 7x's are the same thing. And I'm not canceling them out, but as long as they match, this is what's always going to simplify to. Okay, so what if they don't match? Here I have the limit as x approaches 0 of sine 3x over x. Well, if I can make those match, life would be really good. So I have the limit as x approaches 0 of sine 3x, and I can rewrite that as times 1 over x. I haven't changed anything, but I'm going to make it look a little bit different. Now remember, if I'm working with a fraction, as long as I do the same thing to the numerator and the denominator, everything's totally legal. So I'm going to multiply this by 3x over 3x. That's just equal to 1. So I'm not changing it, but I am going to make it look a little bit different when I do that. And now I'm just going to restructure it a little bit. So I have the limit as x approaches 0 of sine 3x over 3x. So I kind of moved this one, and I'm moving this one, times 3x over x. I keep simplifying, so I have the limit as x approaches 0 of sine 3x over 3x times 3x divided by 3 is just 3. And I know the limit of sine 3x over 3x is 1 times the limit as x approaches 0 of 3 is 3. So this limit is just equal to 3. So my final answer here is 3. Those can get a little confusing, so let's try another one. Now this time it's a little bit different. So I have limit as x approaches 0 of sine 7x divided by 3x. Again, since I see this sine 7x, I really want to get a 7x in my denominator. I can't just throw one in the denominator, but as long as I do the same thing numerator and denominator, this is totally legal. So I'm going to rewrite this a little bit, reformat it. So I have the limit as x approaches 0 of sine 7x divided by 7x times 7x over 3x, right? I just kind of broke that fraction up and moved them over a little bit. So I said, okay, now I can clean that up a little bit more. So this is the limit as x approaches 0 of the sine of 7x over 7x times 7/3. And now I'm going to take my limit. I know the limit as x approaches 0 of sine 7x over 7x is 1 times the limit as x approaches 0 of 7/3 is 7/3. So this answer is just 7/3. So using my limit laws, okay, let's try one more of these. This one doesn't look quite the same. It's the limit as x approaches 0 of sine of x plus 3 over x squared plus 8x plus 15. Well, the first thing I look at, I say, well, x squared plus 8x plus 15, I can factor that. So this is the limit as x approaches 0 of sine of x plus 3 all over x squared plus 8x plus 15 factors to x plus 5 times x plus 3. Oh, well that's fantastic, because I can see I have that sine x plus 3 over x plus 3. They have the same angle, so that limit part's just going to equal 1. So just to make this look a little bit easier to kind of follow, I'm going to break this up. So I'm going to say this is the limit as x approaches 0 of the sine of x plus 3 over x plus 3 times 1 over x plus 5. So again, using my limit laws, I'm going to rewrite this as two limits, the product of each. So I have the limit as x approaches 0 of sine of x plus 3 over x plus 3 times the limit as x approaches 0 of 1 over x plus 5. And now I'm going to actually evaluate it. The limit as x approaches 0 of sine of x plus 3 over x plus 3 is just equal to 1, times, over here, the limit as x approaches 0, I'm plugging the 0 in for x, I get 1/5, and 1 times 1/5 is just 1/5. So this limit is equal to 1/5.